Now we're going to finish up the CPU. We're going to get it to do memory instructions, right? Because remember, we can do all of these. We can't do the memory instructions, right? But we, or the store byte, right? We can't do any of these 8 instructions, but we can do the rest of these, right? And obviously transfer control to the OS or the debugger, that's not yet real because we don't have any of that yet. But, and then obviously load, these are also load instructions, right? So, we just have to be able to do that, right? Cool. Oh, Louis and AUIPC are not yet done. Whatever, we'll get there. So, here we go. We have stuff here. We still have single cycle data path. Remember, it's single cycle data path. And so, what we have to do is we just have to... First, I have to make a memory thing. So, I want to... Hold on. Hold on. Save. Quit. Please. Hello? I'm just going to restart that. Oh, hold on. This is tiny on stream. We go bigger. So we're going to copy the registers over to act as a memory module to memory.v. And so obviously the memory is going to like contain all like caches and whatnot later, but like we need to make something that works and then we're going to make it fast. So module is going to be our memory. And so we're going to take in we're going to take in the memory address, which is going to be a 32 byte number. Hold on, memory address. Store and load. RS1 plus immediate. RS1 S type. RS1 DMIS 12 bits. That's up to 32 bits. Yeah, no, because it could be up to 32 bits. Yeah, 32 bits. So we want the memory address. We want the write value for what if we're writing to something. And then we want the what's its name? We want the writing what do I want to call it? We have write value, write enable. That's what I want to call it. Cool. It should be underscore V because that's what I already have. And then you have the clock, yep. And write value. Cool. So, let's see, we have load byte, half, word, byte unsigned, and half unsigned, and store byte, half, and word. What we're going to do here is we need, well, no, we're going to set this in the control logic, right? So we're going to set which one of these we're storing in the control logic and which one of these we're loading in the control logic, right? Oh, we also need an output for out, right? Cool. So with, we're just gonna have out, right? Because we're only reading one thing at a time, we're writing one thing at a time, right? We're not doing any of that like x86, like, oh yeah, you can read 2 things from memory and write to memory directly, no need for registers. We're not doing any of that. Yeah. And then this is going to be write value. Then so we're going to write value and now I'll just have address on a separate line because that's different meaning, right? And obviously we have write enable, right? So we have 5 inputs here. A Y for clock, a Y for write enable, sure. And so the register for that contains all of our memory. It will... How many memory blocks do we want? Let's just go 10,000. That's probably good. Yeah, I don't know. We need some big number. 100,000. 100,000 blocks of memory. Let's go. And obviously I less than... I'll just set up a parameter. Parameter num bytes. Num blocks. This isn't the memory block. Num words. And I'll just set it to 100,000. As you do. And so here we're going to have num words. I less than num words. Obviously, I trust the simulator is fast enough to be able to handle 100,000. If not, we'll just scale it down, right? If not, we'll just scale it down. And so we are not going to be doing any monitoring because it's just loading and storing, right? So we're going to check if the memory address is the correct one that we expect, right? So we're not going to be doing that. Assign out to be X. What is X? Oh, X is the registers. Yep. X of address. Yep. ADD RESS. And then assign out. Yeah, that's out. And if write enable, if reg write is greater than 0, no, we're just gonna write to the address. If write enable, X of address is gonna be set to write value. I'll do begin and end because that just, I don't know, I like it. I like it like that. And yeah, I'll also do it here. Begin, end. Cool, so that should be our memory module done. Very nice and simple, because we don't have any caching or whatnot. So nvim CPU file list, and let's throw in memory dot v. Let's just compile. Cool, it compiles. Then CPU. In the CPU, we need obviously our memory here as well. And so memory, I'll call it mem, of course. And so in here, we're gonna need a few more wires. So the wire for, I'll call these the memory wires. Wire, obviously they have width -1, colon 0. And so these are going to be mem write val, and then the mem read val. Then I'm going to set and then I'm obviously address, mem address, because we're reading from memory. And then just another straight up wire. I'll just put it here. Mem write back. Cool. So now let's edit our instruction decode to support all of these. Right, so just a whole bunch of memory instructions. Cool, so we have, let's start with, well, we have to store and load, right? So yeah. So opcode for loads, I'll add a few more. Is load instruction, is store instruction, right? Because store will enable write back, this will enable reading, and also write back on the CPU, right? Cool. Then what we need to do is we need to write to those for loading and storing. So these should be output here. Is load, is store. Cool. And so now I'm gonna assign it here. Assign is load to be if the opcode equals opcode equals how do I, okay, I'm not gonna do any fancy optimization here. Nvim CPU 32 apostrophe B. Cool. So this will be 7 apostrophe B. And so we're checking if the opcode is equal to 0, 0, 5 zeros and 2 ones. 1, 2, 3, 4, 5, and 2 ones. Cool. And then for is store, then we're going to do opcode is 0, 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1. So we have is load, is store. Then, hold on. I should probably just modify my branch. Opcode 2 and I'm just gonna do here. We're a branch if opcode is equal to 7 apostrophe B, and it's 110011 110011. Cool. So there's branch is jump and link register 110111. Opcode equals 7 apostrophe B 110011. Wait, 1 1 0 0 1 1 1. Jump is opcode 2 and 6. 0 1 2 3 4 5 6. Okay, so that's just all of the jump ones. Well, you know how it is. Opcode, is that equal to 7 apostrophe? That is any of the jump ones. No, we do want to support both. Okay, cool. That's whatever. Now let's actually syntax error in CPU 3735. Oh, because we have 2 more things here, so we should add some more wires here for is load, is store. I'm going to caps here because that's kind of annoying. Am I using every single possible thing here? Yeah, but whatever, you know. It is load, is store. Line 37, invalid syntax. What is the invalid syntax in line 30? Oh, I didn't fill out the details for memory. Whoopsies. So, semicolon here. So, mem address. Oh, hold on. Mem address, mem write val, mem write back, and mem read val. Wrong number of ports in 35. Expected 5, got 4. Oh, because I forgot the clock. Whoopsies. Cool. Let's make sure I didn't break anything. We're still going down to 36. The numbers look about accurate. Yeah, looks like we're fine. Cool. So we have is load, is store. So we're gonna do a few more assigns for the memory. Assign mem write back. I'm going to assign it to be well, we're gonna be assigning it to is store. And then assign mem write val. Mem write val is okay. So mem write val is store. It's literally just whatever is RS2. It's just RS2. So RS2 would be val B. But it's val B of a certain amount, and that's based on 3. Yes. So then this really should be an instruction decode. Okay, after I build this feature in, what I'm going to do is I'm going to make instruction decode better here, right? So it's basically, yeah, it's basically just I want to get instruction decode fully working if it's there. Yeah, I'm gonna make it not like I want like consolidate all of this into instruction decode, and then instruction decode will like handle all of it, right? So mem write val is if funct3 is equal to, well, yeah, it's val b. Yeah, so yeah, funct3 is equal to 0, then it's val b of 0:7. Well, 7:0, 7:0, right? Because remember, we're doing this backwards. Then we bring it down here. We do funct3 is 1. Then it's val b of 15 to 0. Paste that down here. Replace this with a colon. And then if funct3 is 2, correct? If it's 2, because store would, then we're going to do, instead of 15 here, 31. We're going to store the entire word. Right? Cool. And so that's the write val done, theoretically. And then obviously a nice colon and then a fallback value, I don't know, 0. And it's going to be whatever with mem write val is, which is, 32, which is what we expect. And then mem read val is, that should be, yeah. So in a, no, this is the thing we write to our registers. VL2. Yes, okay, so the names are bad. VL2, jump. If it's jump, we're writing instruction point +4, otherwise it's val right. Okay. Then is load. If it's is load, we're gonna be writing mem read val. Otherwise it's val right, you know? And I'll just put this on another line. And let me align all of these nicely, you know? There we go. Cool. And so that should be mem read val. We should probably have like a how much are you pulling from the memory, and so this is gonna make memory more complex, but whatever, you know? So inside memory, let's feed it in at the end here. Funct3 and vim memory.v, and here funct3. And so when we're reading, yep, assign out is x of address. And so it's funct3 spamming time. If we have funct3 is 0, funct3 is 0, then that's load byte. So we're loading x of address of 7:0. Else, bring it down here. We do a nice funct3 is equal to 1. Then it's load half, so it's 15:0. X of address, and it's going to be 15:0. Colon, enter. Yoink, paste, you know. Then if it's 2, it's going to be 31:0. Then we have 0 extension. Okay, so what I'm going to do is I'm just going to say, how does one do 0 extension? Oh, wait, hold on. We have to do concatenation here. I'll just say a permanent register 0 reg of with -1:0 of 0, and so, and then at the begin I'll also say 0 equals 0. Cool. And so then down here I'm gonna do some concatenation here. So what does load byte just loads the byte directly, whereas what does 0 extension mean for load byte unsigned, or do those sign extend? No, this should just be we take the byte, we put it in direct. What RISCV, what does 0 extension on load mean? Okay, loading of unsigned, zeros are filled in the remaining bits. What happens? Load store. Okay, yes, we have this. Load. 5 memory load instructions. Yes. So, already is a register destination. So if we want to load the word address into T0, we load the immediate into the thing. Yep, this checks out. Yes. Unsigned 0 fills the upper part of the register. Oh! So if we do load byte, we just edit the bottom bit, whereas... Okay. Got it. So, if we do load byte, that just means we are... Okay, so load byte, all that means is that we just like overwrite the certain bit of the thing, whereas this does a full 0 extension. So if you like don't care about what happens to the upper bits, it's like you can just not 0 extend. But like this already 0 extends. Huh? Okay, hold on. Write out. Okay, so this func3 stuff should not be happening in here. this should be happening inside the actual CPU. So we're gonna read the full 32-bit bytes from here, and then in the actual CPU, we're gonna do cutoffs and whatnot. Cool. So that means I will get rid of the func3 that we're feeding to the memory here, because that feels unnecessary. And same for here. We're going to be removing the func3. Cool. And so VL2, instead of memory read val, mem, I'll just set up wire of width -1 colon 0 mem read val, no, not read read, okay, mem read readied val, sure. And so then assign, oh my god, mem read readied val, and so this, and this will be readied val. So this is if func3 is 0, then what we do is register destination is 0 to 7. Huh? Is that just like we don't care? I think that might just straight up be a we don't care thing. So I have a 0 here somewhere, right? No, I don't. Reg with -1 colon 0 of 0. Let's set that to 0 really quick. Cool. There we go. And so where is it? Yeah, ready val. This is going to be mem mem read val of 7 colon 0. Obviously we need here. So 0 of 31 colon 8, because we are not including that. Cool. And then from here, oh, hold on, we need the colon. There we go. We have a func3 equals 1 question mark. Then 0 of 31 colon 16, and then mem read val of 15 colon 0, and then a colon. And then obviously we need 2, and obviously this isn't fully RISC-V whatever, but like, you know, and this one is just mem read val. Cool. And so then I'm just gonna yoink these and then paste it in here and then delete this bit, because I'm gonna be real, I don't actually know what exactly to do. I think it's just undefined behavior, what happens to those bits. So, you know, I don't particularly care. 7 to 0, 15 to 0. 0, 1, 2, 4, 5. Okay. 4, 5, and then and otherwise we're just gonna be doing 0. Cool. 0 is our fallback. Cool. That should be good, actually, surprisingly, because there's only 8 instructions. Cool. And you compile CPU 53 and 52. Unable to bind. 53 is load. Mem. Oh, read. Cool. Yep. Make sure the rest of it still works. Rest of it still works. Okay. Now we need to add memory instructions to our test bench. Oh my god, okay. Whew. So obviously we have our main loop down here that I actually don't particularly care about what goes on. So I'm just going to do a whole bunch of immediate nonsense. So I'm gonna load. Let's use X5 and X6 for memory. Nah, I'll just use these three, whatever. So this is going to add X0. Hold on, I should probably copy the X0 one then. Let's do X3, whatever. Cool. So we're gonna have add I. We're going to do. We're gonna add. We're gonna put it. We're gonna read from memory address at 15, and we're gonna put that into X3, right? Cool. Do these have a special format? S format. Right, because it's in immediate format. Oof. Hold on, we're not done yet. NVIM instruction decode. Okay, so we have immediate I, J, B. Now we need immediate S. Immediate S. Is caps lock on? Caps lock is on. Cool. So we have immediate S. Assign immediate S. Oh, I have to assign it as an output. Immediate I, immediate B. How big is immediate S? Immediate S is literally just immediate B, but right shifted by 1. Okay. That's... No, it's not. It's very different. It's in the same spots, though. It is 11 to 0. Yeah. Immediate S. Cool. Then in here, it's going to be instruction of 31 to 25. Concatenated with instruction of 11 to 7. Instruction of 11 to 7. Cool. That's very nice, actually. That's very nice. Cool. Now, immediate I. Now, immediate I, B, S. And then for memory address, it should be... Well, okay, hold on. Where are we assigning memory address? We are not even assigning memory address anywhere. This is actually fine. Assign mem address, and that's going to be equal to RS1 plus immediate. Yep, RS1 plus immediate. So val A plus, and then we're gonna have a ternary operation here for is store. No, we're gonna do is load. Load. If it's load, we're going to do immediate I. Otherwise, immediate S. Right? Because if it's load, we do I format, which is here. And then otherwise, we do immediate S for S format. Cool. Make sure I type it right. Wrong number of ports in CPU line 35. Right? Because I need to set up immediate S here. Immediate S. Compile. Yep. Everything else still works. Everything else still works. Cool. Now we can do our stuff. You want that in from there. Paste it before the loop. We're going to do all memory operations before the loop. And then from there, we should have memory all done. All good to go, you know? And so what we're going to do is we're going to do... Yeah, so we're going to store in our address. We're going to put it into address. It's going to be 3-digit number. 854 into X3. So we're going to store a word because we're going to store all of them as words, as is usual. RS1 is going to be X3. RS2 is going to be X4. And so we're going to store a magic number 1024. Sure. And then we're going to have a loop in here where we just like... I'm not going to decrement 1024. Hold on. No. We're not doing that. We're going to store the number. So we're gonna put this in X4, and we're gonna store the number. No, let's do 854 here, and let's do memory address 512. Yeah, memory address 512, just to make our lives easier. And obviously, I gotta change this from X3 to X4. RD comes just before the opcode. Yep, 1, 2, 3, 4, 5, 6, 7. So instead of 3, it'll be 4. Cool. And so we're gonna add. Oh, we have to change the number. Okay. So this is an I format, so it's straight up just the numbers here. So we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. And the rest of this is just immediate. No, func 3. 1, 2, 3. 1, 2, 3, 4, 5. Cool. So there's the number. So we need to add 512. So this is the 1 spot, 2 spot, 4 spot, 8 spot, 16, 32, 64, 128, 256, 512. That might have been 1044. It's either 512 or 1024. It doesn't actually matter. We have enough memory for that. Whatever. Cool. So this is going to be some number. Hold on. There's potentially up to 12 bits. 12 bits here. 2 to the 11 is 2048. 2048, 1024, 512. Yeah, 512. 854. Alright, let's do some math. 8 calculator. That should be big enough. 854 minus 512. 342, so we need 256. Cool. Minus 256. 86, so we need a 64. So that's 256. 128, 64. Not E. Minus 64 gives us 22. So we need 32, 16. Right, so that's 16. Minus 16 gives us 6. So that's 8, 4, 2. Cool. So we've written 854 into X4. The exact number I don't think matters, because we're going to write to X4, then we're going to read that number into X1. Yeah. So we've wrote it there. So then we're going to do a store byte. Not store byte, we're going to store word. We're going to do a very nice store word. SW. Store word. And then inside of store word, we're going to. So store word is. It just says RS1 and RS2. Yeah, so the value. So we're going to store word with RS1 being the RS1. So RS1 is the address. So RS1 is going to be X3. RS2 will be X4. And we're just going to 0 for that immediate. And we're going to store it into. Well, no, X3 is the address. There we go. Cool. Because it's a store. Right? So X4, and we're going to store into X3, 0. Cool. Now we have to manually edit all of this. Cool. So store word is 11110001, and then 0. Cool. Then we get immediate. So this is 0. 1, 2. So hold on. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. Because there's 5 bits there. Then we have func 3. For store word, func 3 is 2. So 0, 2, func 3. There we go. Then we have RS1. So RS1 is our. Where is it? RS1 is our. We're going to store it into this memory address. So it's going to be X3. Cool. So X3 is 1, 1. 1, 1, 0, 0, 0. Then we're going to have our RS2, I believe. Yep, RS2. So it's 4, 0. So that's 1, 2, 4, 8. Yep, there we go. And then the last bit of our immediate is just 0. 0, 0, 0. Cool. So there's all of that. So we can store the word. Now we're going to load the word. You know what? Let's load. Yeah, let's load the word. Yeah, let's load the word. Yeah. So load word is the same thing, but without this one. So 7. Then load word is again func2 of. Sorry, no, it's not. What is load words? Load word gets it's load words I format. So that means it gets an RD. Oh, I should probably set this up. We're gonna load word. We're gonna load from x3 of 0, and we're gonna load into x. And yeah, so what are we gonna load into? We're gonna load into x1. Yeah, there we go. So 1, 2, 3, 4, 5, 6, 7. Then destination is x1. So 1, 2, 3, 4, 5. Then func3, 0, 1, 0. Then it's going to be rs1, which is x3. rs1 is our address here. Yup, it is rs1. 1, 1, 1, 2, 3. And the immediate after that. The rest of this is just immediate stuff. Yep, no rs2, just an immediate. Cool, so there's store, load. We should see that load and we just jump back. Cool. 52, 56, 60, 64, 68, 72. So let's compile. CPU 28, 29, 30. Ignoring out of bounds. Oh, my instructions aren't big enough. Okay. Parameter. IMEM size. Let's go 10,000. I don't know, I don't particularly care. IMEM size. But it should be IMEM size -1, whatever. It doesn't actually matter. Cool. What numbers do we get here? F3. X3 gets a crazy number. And X1 gets 0. What? Why is our X3 kind of insane? And why are we jumping back to 36? Okay, whatever. Okay then. What is going on at 52? 52 is loading the immediate. Oh, we're printing it out as signed when it should be unsigned. Ah, hold on. Memory.v. Input. Unsigned. Input write value. Unsigned. Because we don't actually care. We're just either reading or writing. Output is signed. Well, it doesn't actually matter. Because it's just the value in the address, right? Cool. When we print out x3, we should probably be printing out. Hold on, why is this I format? Hold on. Load immediate. Hold on, not load immediate. Add immediate. Immediate. Okay, so it is signed. Oh, it's signed. Wait, no, signed is fine here. Why is the value in x3 some crazy number? Hold on. It's I format. Immediate 11 to 0. CPU test bench. Where is our add I? X0, 512. 1, 2, 3, 4, 5, 6. Immediate is 12, right? So that should be correct. There's a whole bunch of zeros here. And RD, and then just zeros. There's so many zeros here. That should just be correct. 001, 0011. 001, 0011. Okay, why is x3 wrong here, but it's correct at the very start? At the very So we do in fact write 11 into x3 and we just don't touch it, right? So that is correct. Why is this wrong? Because here, whole bunch of zeros. Why is our 11 starts here? Hold on. Let me add a space here so all the numbers are nicely lined up. So that's where the 11 starts. Whereas here should be 512. So 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. That's correct. Add I, x0, 512, x3. Why are we just writing 16 to it before? Okay, we're just doing a random x3 test. Sure. So we should be writing 16 and then 512. Do we see that? Yeah, we are writing 16. And that's a crazy number. What? Okay, hold on. Let's see what bit does this actually break? 256? 5949. Okay, it is a different number. Huh? So, okay, hold on. Let's do 16. 16 does in fact work. So, okay, at least we're finding this bug now, you know? 32? 32 breaks. Why does this only support 5 bits? The write back value, if it should just be, not memory, value 2, should just be val write because we're not doing loading, right? Because is load only based on the opcode. So we're doing val write. Let me display val write. Always. And then I'm gonna do display val write, yes. Let's just compile, /test. Val write is... Why is val write some crazy number here? Val write is a crazy number. Where do we set val write? Val write is set from the ALU. Okay. And because it's immediate format and it's add, val write is the ALU output. Why is the ALU outputting a crazy number here? What is val A in A? What? I should really rename in A to in B. I'm gonna do that now. In A, in B, in B. Cool. What is the value going into in A and then in B? Oh, hold on. Oh, whoops. It's not in A here, it's in B. And in B should be the one containing our immediate. So here we have 16, then 32. Okay. So that's correct. Then what's going into val A? Val A. Val A. / compile. / test. Then here 0. So 0 plus 32 should get 32, correct? That checks out to everybody? ALU.v. Cool. Func3 and Func7. Okay, we should probably print out Func3 and Func7. I mean, why would those be wrong? Okay, you know what? I have no trust. F3. Func3, Func3. / compile, / test. Cool. Func3 is 0. Func7. Func7. Func7 here is also 0. Right? Okay. What? Okay, Func3 goes... Oh, Func7 goes kind of insane there, but that's whatever. Okay, sure. The ALU output val right is bad though. Right? PW, val right. Val right, comma, val right. Val right here, 16 is just an insane number. ALU.v. Unsigned input. Oh. Wait, but 32 should not make signed. It is unsigned information. Right? Hold on. Add immediate. It is just, we're just adding RS1 and the immediate. I'm just gonna print out. Yeah. Func3 and Func7 are both 0. And it's gonna be dollar display. I don't like monitor anymore. I like display. Out. I'll write ALU out, and then I'll just do outcome out here. Unable to bind clock, right? Because you don't use clock. Huh. Okay then, so we can't do that. We just have to trust the output of here. So we're feeding in the right numbers into the ALU, right? Val A in B, Func3, Func7, and val right's an output. Why is val right wrong? Huh? Should be, and then I'm just gonna do a percent sign H, percent sign 0D here, and then so we have val right, and it should be the val A plus in B. Val A plus in B. File, that's test. Missing argument for display. U. Okay, hold on. Val A plus in B. Val A plus in B. Okay, cool. There we go. That's compiled. That's test. Okay, we have a lot of information. Here we go. 16 should be 16. Crazy number should be 32. Why is it not 32? That looks like it's 0 minus 32. Why is it subtracting the numbers? Hold on. Why is it subtracting numbers? Oh, is it because it thinks it's sign? No, sign shouldn't change it because add is just add, right? Because overflows would turn it negative. Wait, huh? Why is it thinking to subtract instead of add? Huh? Hold on. Well, let's just not do... ALU 18. Oh. Okay, I'll put this back here. Huh? Okay. Okay, let's disable subtraction from the ALU. Let's make sure let's have it so we cannot subtract anything. And let's see if that works. That does work. Does it? Instruction pointers, 32 should be 32. Yeah, that does actually work. And then obviously writing and reading is what it is. I don't particularly care about that so far. Why is it going down a subtraction route instead of the addition route? Because it was working just fine before. Huh? You test bench.v. Probably should have done way more testing earlier, but you know, it is what it is. 32. Okay, I'm gonna rewrite this to be 32. So 32 is a number that's too big for this. Because... What? So we're adding 31, and that works just fine. That does, in fact, go to 46 at the start. Correct? Right? At the very start, big amount print, it goes to 31. Huh? Oh, hold on. Is this just bad writing? Oh, this should be x1. X1, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5. Then func3 for I type, yep. 1, 2, 3. What? Why are we shifting left by 32? Oh, wait, what? 15 is 1, 1, 1, 1. 31 is... Hold on. Huh? 1, 2, 3, 4. What instructions? 5, 6, 7. Yep. So 0, 0. So 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Yep. Okay. So we're in this area. Destination register. 1, 2, 3, 4, 5. Yep. X2. This is correct. Func3. 1, 2, 3. Correct. X1. 1, 2, 3, 4, 5. Okay. So we're adding 31 to 15. Sorry, we're adding 32 to 15 and we're somehow getting 31? What? Could it be... Huh? NVIMs... Hold on, is it the opcode we're feeding into the ALU? No, we're feeding in func3 and func7. And func3 and func7 are the correct numbers, right? We know this to be true. Func3 is there, and func7 we normally don't care about. Why is func7 a thing we normally don't care about? Because we don't care about it there. Oh! I know exactly the issue. Okay, that... Honestly, that checks out. That checks out a lot. NVIM... Okay, that checks out. It's because we were writing to func7 in that instance, because, yeah. Instruction decode.v, where's func7? There's func7. It should be... How do we know? We just have to figure out if it's R format. I'll just set up a wire in here. Is R format. Wire is R format. It should be is R format question mark this, otherwise 0. And then if is R format, how do we decide it is R format? Well, what I do is I say, I mean, it's literally just the opcode 0110011, right? Assign is R format to be 011 0011. I should probably do func7 apostrophe B. Cool. What does this start out as? 0, 31. This should not be 31. And vim instruction decode.v. Okay. Func7 is, if it's auto format, we set it to be func7, otherwise it's 0. 0, 1, 1. Okay. Use auto format is 0, 1, 1, 0, 0, 1, 1. Yeah. Huh. RD, func3, RS1, RS2, func7. Func3 exists in most of them. U-type and J-type. Okay, I haven't done U-type yet. And J-type, I think my logic ignores func3. Yeah. Okay, hold on. Well, clearly it works. So func7 is our format. And is our format. Oh. It's not big number. It should be what's it called? It should be opcode equals, there we go. Okay, what are these numbers going to? Still at 31. Huh. So we have the 15. Yeah, that's correct. Wait, the big number's not there. Okay, so it is working. So why is this immediate not adding two numbers together? And vim cpu.v func3 and func7. F3 and then F7 equals, and I'm just gonna, well, we don't care about F7. Func3, func3, func7, func7. Cool. And so now if we go all the way up to the start, we can see they are literally both 0. Okay. Let's go val 8. Well, we're reading, yeah, so it should be val 8, yep. Val A, and then here it should also be val A. Just compile this as test. And then all the way up here. Cool. I should probably delete the instruction pointer printer, but yeah, whatever. 15, yes, this is correct. Then what is in B? I'll go over here. In B, and what else do we want? We want VW for val right. So then in B, val right, val right. Cool. And then all the way at the top here, we will have in B is, hold on, in B is 10, val right 31. 16. Oh my god. Yeah, that checks out. I just wrote 16 in the instruction. Yeah, because that's 15 plus 1, 16. Okay, there we go. That should be corrected now. Cool. Now, I'm going to delete all of my random prints. Yeah, 46. Yep. Yep. CPU.v. Cool. Let me delete a bunch of my random prints. And by delete, I mean comment them out. Because I like my print debugging, you know? Cool. And then obviously $display and vim CPU test bench. We have a display in here, right? Monitor, yeah. Cool. Let's compile. Let's test. Yep, we just had a nice list of values here. I am undoing the commenting here because I like seeing the instruction pointer. Cool. Why are we stuck in a 12-16 loop? Branch greater than or equal. Oh, we set the number to be bigger. Okay, you know what this means? Oh, is the number actually decrement? 38, 39, 40, 41, 43. Oh, we have to... Okay, how long do we want the thing to go on for? Let's say 240. Our while loop was going on for a lot longer. Okay, there we go. 11. Okay, cool. We're writing 32 to x3. Good. x3 gets a random 72 for 68. Oh, because that's the next instruction after this. Yeah, that checks out. Instruction pointer 36. Go back. X1 gets set to 0 during all of that. Okay. So our load word is not correct. So now we have to debug our memory. Cool. If we write to it, let's just say $display, and let's write the right value. Right value %sign D will be 0, 1, comma, right value. I'll do %sign 0 D, yes. We fancy today. Oh my god, malformed statement in a whole bunch of stuff. Memory v30 error. Oh, I forgot a semicolon. Whoopsies. We're writing 854. This is good. Memory.v. Display, and then write enable is on. We know this. Let's display the address. It should be address 32, right? ADDRESS. Cool. Let's compile. Let's test. Address 4. Address 4. Okay, so we're writing to address 4 and we're reading from address 32, looks like. Why is our write address wrong? Store byte. Is our immediate S format wrong? Okay, back print debugging. I'll put IS. Immediate S. Immediate S. Okay, cool. So we have immediate S. Printing here as well. IS. Okay, so immediate S is 344. Why? Oh, immediate S is 0. This is correct. It should be no. Hold on. Right. So that's well, let me go into CPU test bench. So in here we are storing. Hold on. So we have add immediate. So that that checks out. 854. Then we're storing it. So we should have 0 0, and then we should have the jump. Right. So that makes sense. So storing 0 0, and then we have the jump. Yes. Cool. Why is immediate? So immediate S is correct, right? NVIMs. Let's just read the address. Hold on. So we have immediate S address, right? So let's just straight up read the address. ADDRESS, right? So compile. Unable to bind. Huh? Oh, mem address. Whoopsies. Memory address. compile, also has test. Okay, so why is mem address 4 instead of the expected 32? Because what we're doing here is 0 plus 32, are we not? Oh. Where is mem address? Mem address is val a plus immediate s or immediate I, yeah. So what is our val a? VA. Val a, and then here it's also val a. Val a, cool. Let's compile, let's test. Val a is 20, yeah. Address is 4. It should be 20 plus in B. No, not in B. So val A should be 20. Hold on, mem address. 20 plus immediate I or immediate S based on is load. If it is load, it's immediate I, otherwise it's immediate S. Immediate S is 0. So 20 plus 0. On val A is signed, which shouldn't matter. Immediate S. Oh. It's compiled, also has test. Why is address 4 here? It should be 20 plus 4. Sorry, 20 plus 0. Why is it 4? Hold on. nvim cpu testbench.v. Okay. So in here, what if instead of 32, let's just move it left 2? Right, maybe this is all crazy misunderstanding. Address is 64 here. Okay. Sure. So we're writing... No, address still 4. Okay, so we're ignoring the value in x3 here, and we're just writing 4. Oh my god, hold on. Hold on. We have mem address. And then instruction pointer. No, hold on. Mem address is the one we're reading. 20 plus this. Hold on, let me parentheses around the entire ternary. Why is mem address just 4? We only use it in like 2 places, yeah? Yeah. It was a parentheses around the ternary. And we... Oh my god, it's parentheses. It's always parentheses. Cool. There we go. Hold on. There we go. And let me delete that line. Also compile, also test. And there we have it. We are writing to memory. We're reading from memory. Let's read bytes. So load word. So we're not just going to load words here. We're going to load a whole bunch of stuff. So we need to edit the func3, which occurs immediately after the RD. So 1, 2, 3, 4, 5, 6, 7. X1, 1, 2, 3, 4, 5. Then here, so 1, 0, 0, 0. So load word, load half word, load byte. And the number I'm going to load into X4. Load. Okay, so immediate can only do this much. So I'm gonna have to like somehow generate a massive number, which I'm not gonna do. So I'm just gonna test load byte here, see if that works. And that works, load half probably works, right? So instead of this, I'll just add a 1 there. So 854 plus 2048. 54 plus 2048 is 2902. We're going to load in 2902 into x4 down to 86. Why is it always 86? Oh, okay. The memory address is in fact here. We're going from some number to 86. Why is it 86? They keep telling me that this number is 86. I do not know why it is 86, you know? CPU dot v. Hold on. Write value is in VL2, so let's do some more print debugging. Valet mem address. Cool. So we are continually writing 86 here. Yeah, the address is all correct. Why are we writing? Oh, hold on. So we should be printing out the VL2. And so I'm just gonna bring it in here. VL2, comma VL2. And then here, what we're gonna do, we're gonna print out VL. What are we gonna print out here? We're gonna print out the. So that's the number that we're actually writing back. And then we're gonna print out mem read readied val. Yeah. I'll just do mem read val. And then I'll just do it here as well. So what are we getting from memory and what are we actually writing back? Mem read val. Missing argument. Oh, I need to do that twice. Whoopsies. Mem read val. Cool. And there we go. We had some latent prints. Okay, so mem read val VL2. Instruction pointer we care about is 68s and whatnot. VL2. Mem read val 2902, 2902. Is there another 2902? There's just two 2902s. I'm writing 1 or 86. Oh, wait, hold on. This is when we're writing. This is the write statement. So we're writing 2902. Then we're reading 2902 and we're 86. We should have... Oh my god, we're rewriting all of these. 68, 72, 76, 80. Okay, and the rest of my print statements are annoying here. And whatever. Compile loss as test. What are the numbers? 2902, 86, 2902, 2902, 86, and then we do whatever we're doing. Cool. That's really nice, actually. Because this means load half works, and so that means I assume load word works. Unless I really want to just do like, hey, we're going to iterate above a 16-bit number. Let's go, guys. But this means all of my loads and theoretically all of my stores work too. Which is a very nice sign. You know what? Let's test the stores as well. All right, let's test the stores as well. So we're gonna in here instead of store word, what we're going to do is we're gonna store byte, and we're gonna store correct byte, and then y2j, and we're just gonna print out all three of these as well. So 60, 72, and then 76. 80, 84, 88, 92, 96. That says compile, that says test. 2902, 2902, hold on, where are we at? Yeah, 2902, 20, let's go up to here. 2902, 2902, 86, 86, 86, 86, there's a bunch of 86s. And there we have it. Why is x3 96 here? Okay, so that's a start. Oh, goes up to one. Oh, it just goes up 128, and then we do a whole bunch of writing to it, I assume? 60. It doesn't go ever back. What's Oh, we're only going back 9 instructions. Oh. Hold on. We're only going back 9 instructions, so 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're not touching x3. Why is it causing me issues? 2, 3, 4, 5, 6, 7. Whole bunch of zeros. X3, X4, and then just the rest of it is zeros, yeah. Oh. Forgot which one was func 3. Whoopsies. 1, 2, 3, 4, 5, 6, 7. And then let's go back to RISCV card or store byte, which is S format. Here we go. Opcode, we have the immediate for 5. 1, 2, 3, 4, 5. Then func 3. 1, 2, 3. What? Func 3 and RS1, and RS1 is obviously x3 here. So it's 2. So let me set this to 0. Store that into memory, and then we should be able to just load it all back, right? Would half byte, yeah. And then that's x4. We have x1. Why are we loading this into x0? Hold on, where are we saying this is x1? Oh, because RD. X1 is here. The rest of this is just immediate nonsense. Compile test. Okay, why is this dropping to 96? Where is this dropping to 96? Dropping to 96 at instruction 92. Oh, because that's the next instruction. We don't actually edit it. We're still writing it to memory, right? Yeah, okay. So that's instruction memory. Okay, so we would have been rewriting a code there, which is not great. But that's the cost you come when you're writing kind of bad assembly, actually. So, you know, Okay, so jump and link. Jump and link is J-type. Oh, dear God. 36 does fit within this amount, though. So I'll just... we will go back a little bit further. This should be minus, let's find out. Does this break? Permanently set to 96. So that's 36. And we go back. Where do we go back? Where do we go back from here? We go up and then we go back down to 60. Checks out. Okay, and then I want to go back a little bit for like 4 more. So going back 4 more would require subtracting this number by oh, we have to go back like 8 more, so minus 8. So you have to subtract 8 from this number, which implies subtracting, wait, 1, 2, it goes from 1, so 2, 4, 8, 16. So 2 plus 4 plus 8 plus 16 is 36? No. Hold on. So we're doing 36 here. What happens if I set that to 1? We are going... Huh? Hold on, 128. 96. 62, so we're going 30. That was a 4-bit actually. Ah, so that's 2, right. 36, the 2 above, what's it called? Yeah, whatever. So we need to be going back a little bit more. That bit has to always be set to 1. 0, 0, 0, 0, 0, 1, 1, 1, 1. And so we've increased that by 4, right? And so then that should be 1 more. So I should set this. I don't know if I'm making sense here. I'm gonna be entirely real, but we'll see. 128 to 96. We go back down to 56. What is in byte 56? 56 is this. Oh, we have to go back a little bit more. So like another 4. Or 8. There we go. 120, 96, and then we overwrite it with 128. There we go. Nice. The problem's with my assembly code, not my normal code. Cool. Yeah. That's really nice, actually. We are able to have nice loops, right? Because we iterate a number and we wait. And we have all the arithmetic operations. We can load, we can store. That's really nice, actually. I'm going to stop the stream here. That was a great success today. We're able to do oh, no, I'm not done. I'm not done, actually. We're not done. I still have to do load upper immediate and add upper immediate to PC. So U format instructions. That's how you, yeah. Yeah. I'm gonna do that off stream, actually. I don't want to do it on stream. But other than that, we should have everything. Thank you very much for watching. I will see you all later.